In this module, we will discuss the uncertainty principle. So before doing so, let us set the stage first by briefly recapping what we've already done. So remember that the way you understand the act of measurement and predicting the probabilities follows a two-step process. The first step is to prepare the system in some state psi. Okay. Now let us say that we want to measure an observable A, which is represented by some Hermitian operator A hat. And let us say for simplicity that A hat has two eigenfunctions and two eigenvalues. A psi plus equals A plus psi plus, and A psi minus equals A minus psi minus. So on this system psi, we are interested in measuring A. So I want to know how A acts on psi. The operator A acts on psi. To do that, it is useful to use the superposition principle and decompose the state psi into some linear combination of the eigenfunctions of A. So I can write psi as some alpha times psi plus some beta times psi minus. Okay, so if I do it this way, then the action of A on psi is very simple to understand. It is the action of A on alpha times psi plus beta times psi minus. And since A is a linear operator, I can pull out the alpha and act it on the psi plus and so on and so forth. And this becomes alpha A psi plus beta A psi minus. But I know how A acts on psi plus and psi minus. They are the eigenfunctions of A. So this is equal to A plus alpha psi plus A minus beta psi minus. So the measurement of A on the state psi would either give me A plus or A minus, and the probability of A plus is the absolute modulus of alpha square, and the probability of A minus is the absolute value of beta square. Okay, so this you already should know by now. Sorry. Okay, so now let us proceed and ask a slightly different question. So let us say that we have prepared the system in some state psi and we have measured A. Okay, let's say we have measured A on psi and gotten the value A plus, right? So this means that the state of the system immediately after measurement has collapsed to that particular eigenfunction psi plus. So the state of the system right now is not psi but psi plus. Okay. So now let us ask the question, what happens if we try to measure something else on this state psi plus? Okay, so let's say there is another observable B. Okay, corresponding to B, there is an operator B hat in quantum mechanics. Now I want to understand that now that I've prepared the system in state psi and measured A and gotten the value A plus, thereby collapsing the system to state psi plus, what happens if I try to measure B on this state psi plus? So what happens if I try to measure B on this state? Okay. Now, in general, there is two possibilities. First possibility is this. The first possibility is that psi plus is also an eigenfunction or eigenstate of B. The second possibility is no, psi plus is something completely different. Psi plus is not an eigenfunction or eigenstate of B. We'll look at these two possibilities separately and work out the consequences of these two possibilities. We will simply do this pictorially. Okay. Now, what am I saying? So let us say that B is also some operator that has two eigenfunctions and two eigenvalues. In general, let us say that B has two eigenfunctions, phi plus with eigenvalue B plus, and phi minus with eigenvalue B minus. Now the first possibility says that the phi plus and phi minus are nothing but psi plus and psi minus. In other words, it says that A and B share the same eigenfunctions. We'll talk about operators that actually have this property. Two operators can have the exact same eigenfunctions. In the language of matrices, two matrices can have the exact same eigenvectors. They would have distinct eigenvalues in general, but it is possible for two matrices to have the exact same eigenvectors under some condition. We will discuss what this condition is in a second. Now, what happens to the act of measurement if the state psi plus, which is an eigenstate of the operator A, also happens to be an eigenstate of the operator B? Well, let's do this schematically. So first, I start by, let us say I measure A, okay? And I get A plus, which means the system has now collapsed to the state psi plus, which is the corresponding eigenstate of A. Now, immediately after this, I'm measuring B. Now, if psi plus is also an eigenfunction of B, then on this state, B is going to give me the value B plus, right? Because B acting on, if phi plus is the same as psi plus, B acting on psi plus is B plus psi plus. So if psi plus is also an eigenfunction of B with some other eigenvalue B plus, then upon a measurement of B on psi plus, I'm sure to get the value B plus. And I will put this word sure in a firmer mathematical footing as we move forward. Now I can keep going. I can again, now that I've measured it to B plus, the system has collapsed to state psi plus, which is the eigenstate of B. I can again measure A. And again, since psi plus is also an eigenfunction of A, I will 100% get A plus. And then I can keep going this way. So if you have two operators which have common eigenfunctions, the act of repeated measurement of both in any order does not change the state of the system. The state of the system is the same because they are both the same, they're both eigenfunctions of the same operator. So you're going to simply get the corresponding eigenvalue over and over again. Okay. Now what happens if psi plus is not an eigenfunction of B? Well, if psi plus is not an eigenfunction of B, then we have to go ahead and do this exact same calculation again, exactly like this and like this. How will I do this? Well, again, I will write psi plus as some linear combination, some alpha tilde phi plus plus beta tilde phi minus. Okay. Now I'm not sure to get one particular value. I'll get either either B plus or B minus with probability. The probability of getting B plus would be alpha tilde square. The probability of getting B minus would be beta tilde square, right? So suppose if I start out and try to measure A on some state and I get A plus, now I have collapsed this to state psi plus, and on this state, if I measure B, I'm not sure to get only one of the eigenvalues because this state psi plus is not an eigenfunction of B. I can either get B plus, okay, sorry. I can either get B plus with probability alpha tilde square, or I will get B minus with probability beta tilde square. Okay. Now, if I get B plus, then I have collapsed the system onto the state phi plus. And if I get B minus, I've collapsed the system onto the state phi minus. Then I can play this game over and over again. I can write phi plus as a linear combination of the eigenfunctions of A. And if I want to understand what happens if I measure A on this, I can write phi plus as a linear combination of the eigenfunctions of A, and I can compute the corresponding probabilities and so on and so forth. So you see that the flowcharts A1 and 2 are completely different, right? if A and B have common eigenfunctions, an act of repeated measurement of the two will not change the system state from one to the other. But if A and B do not have any common eigenfunctions, then the act of measurement will in general change the state of the system at every intermediate step. Okay, assuming that you're measuring A and B repeatedly. So this idea that two operators can have simultaneous eigenfunctions is an important one. Okay, so the question is, what kind of operators have simultaneous eigenfunctions? It is much easier to see this in the context of matrices, and you probably already know the result. But let us do a quick aside and consider two matrices A and B. Okay, so they have two matrices A and B. Okay, with the nice property that the commutator of A and B, which is AB minus BA, equal to 0. Let's assume that I'm looking at two matrices that commute. Excuse me. If I have two matrices that commute, then the claim is that they have a common set of eigenvectors. Let us understand how this is. So let us say that A has a set of eigenvectors, I'll call them phi n, with a set of eigenvalues, I'll call them an. Okay, these are the eigenvalues and eigenfunctions of A. Now, if A is a 3 by 3 matrix, it is 3 eigenvectors and 3 eigenvalues and so on and so forth. So n basically keeps track of which eigenvalue and which eigenvector I'm talking about. Now, let us multiply both sides of this equation by B. Now, notice that these are the only possible eigenvectors of A. All eigenvectors of A I have already discovered. They are phi n. Okay. Now, let's multiply both sides of this equation by B. So, B A phi n is A n phi n. Okay. All right. Now, since A and B, sorry, A, B acting on phi n. Right? Now, since A and B commute on the left-hand side, it really doesn't matter if I write BA or AB. They are both the exact same things, right? So I can switch the order on the left-hand side and write this as A acting on B times phi n equals AN times B times phi n, right? Now, what is this equation? B is a matrix, phi n is a column vector, B times phi n is another column vector. So this basically is saying that A acting on a column vector B times phi n equals AN times the same column vector B times phi n. But this is precisely the eigenvalue equation of A, right? So this basically says that the column vector B times phi n is an eigenvector of A. But we've already deduced all the eigenvectors of A. They are phi n. So the statement, the equation 1 is telling you that we have discovered all the eigenvectors of A, which is some 3 by 3 or 4 by 4 matrix, and we know all these 4 eigenvectors. But equation 3 is telling you that no, you also have another set of eigenvectors which are B times phi n. So the obvious conclusion is that the vectors B times phi n are not unique. They have to be the exact same things as the phi n over there up to a numerical constant. So the conclusion from the equations 1 and 3 is that the column vector B times phi n has to be proportional to phi n itself, right? So if phi n's are the eigenvectors of A, and if B times phi n are also the eigenvectors of A, then the only way these two statements can be compatible is B times phi n is proportional to phi n. So I can write B times phi n equals some Bn times phi n. But now, oh, I messed up my order completely. So this is actually not 3, but 2. Yeah, okay. Now look at equation 3. Equation 3 is nothing but the eigenvalue equation of B. So equation 3 is basically claiming that phi n's, which are the eigenvectors of A, are also the eigenvectors of B, but with some different eigenvalues Bn. Okay. So the conclusion from this short proof is that if you have two matrices A and B that commute, they have a common set of eigenvectors. The eigenvectors of A are also the eigenvectors of B. Okay, the same is not true about the eigenvalues. The eigenvalues of B corresponding to these eigenvectors are different from the eigenvalues of A, but the eigenvectors are common to both. Okay, so this is not a surprising fact. So when I claim that the eigenfunctions of B are the same as the eigenfunctions of A, it is not a very surprising fact. It is actually a commonly known property of matrices, and in general, a commonly known property of operators in quantum mechanics. So if two operators in quantum mechanics commute, then they have a common set of eigenfunctions or eigenvectors. Okay, so the notion of two operators commuting or not commuting is actually a very important property in quantum mechanics. And this is the property upon which the statement of uncertainty principle is based. So the statement of uncertainty principle is this. Suppose if you have two operators A and B, then sigma A square times sigma B square would be greater than or equal to, I'll first write this down and then we will understand what this means. 1 over 2i times the expectation value of the commutator of A and B quantity squared. Okay, so first to understand this, we have to understand what sigma means, and once we understand what sigma means, we have to understand what this statement means. This is basically the statement of, this is sometimes called the generalized uncertainty principle. Okay, so let us try to unpack what this means. Before we do that, let us try to do this in steps. I'm sure some of you already know what sigmas are, but for the sake of completeness, let us try to briefly revisit the age-old example that we started with when we started discussing probability in this course. So this is a mathematical aside. Okay. So we'll introduce the concept of variance and standard deviation. So remember, about 5 or 6 lectures ago, we introduced the notion of probability by talking about the distribution of some number or ages of people in a room, right? So this is taken from your textbook, Griffiths. Okay, so you can have some kind of so there is some number of people in the room, and there is some probability distribution, Pj, okay, which is given by the number of people with some age j divided with the total number of people. Right? This is a very, very simple discrete distribution. Now let us suppose that there are 2 rooms with a whole different bunch of people in either room, and let us say that you have these 2 distributions for these 2 rooms. So let us say this is room A and this is room B, and I am plotting n of j on both y-axis, okay, and the x-axis, of course, the age j. Now let us say in the first room I have a distribution that looks very different from the distribution of B. Let us say that in the first room, I have a distribution that is very sharply peaked at some value. Okay, and in the other room, I have a more or less uniform distribution of ages. Okay? It doesn't matter what these actual numbers are. Basically, what we are trying to say is that in the first room, there is a sharp peak in the number of people with a particular age. And in the second room, there is a uniform distribution. There is 10-year-olds, 20-year-olds, 30-year-olds, 50-year-olds, 60-year-olds, everything. But it is very possible that these 2 distributions, they have the same average, they have the same median, they have the same most probable distribution, the most probable value, and all those things. Everything else is the same except for the spread in ages. Okay. it is certainly possible to come up with a set of numbers that has the same average but has a wider spread. All right. So how do you quantify this spread? So one way to quantify the spread is to look. So in the first case, everybody is very close to the average, right? So if the average value, so let us say the peak is at like 25, and there is a few people with age, let us say 22, few people with age say 27, but there's a lot of people with the age 25. So if I look at the difference, and I'll call this delta J, from a randomly picked value J and take the difference from the average J in that particular room, for the first guy, I'm going to find that this is very close to 0. And the second guy, I'm going to find that this is not 0 at all. But this turns out to be not a very good measure, because I cannot go on computing delta J for every guy. I should take the average of delta J. But if I take the average of delta J and assume that this is a good measure to characterize this spread, I'm going to get 0. Okay, you can quickly prove that this is true mathematically, but you can actually see that this is true, because in the first case it's going to be 0, or in the second case it's going to be 0, because there's going to be as many people that are above the mean as there are below the mean. Okay, so the average value of delta J is always going to be 0. So a better way to characterize the spread is not to look at the average of delta J, but to look at the average of delta J quantity squared. The average of delta J quantity squared in general is not 0, and this is a very useful measure to understand how to characterize two distributions that can have the same average but are spread in very different fashions. And this turns out to have a very nice and easy formula, and delta J quantity squared average is actually equal to the average of the square of the ages minus the square of the average age. Okay, this is very easily proved. Simply plug in the definition of delta J in this formula and evaluate it, and you will get this particular equation. This is a very nice way of calculating the spread in the distributions. So this has a very nice name, and this deviation squared average is also called variance, and this is called sigma square, J square minus J average square. This is called variance, and the square root of this variance, which is sigma, is called the standard deviation. So the standard deviation is a measure used to understand the spread in the values. Okay, so let's go back. So basically the uncertainty principle tells you that if you have two observables A and B, and if you look at their measurements, and if you look at the spread in their values, and assuming that these two operators A and B do not commute, then standard deviation of A times the standard deviation of B can never be 0. If the commutator of A and B is not 0, then the standard deviation of A times the standard deviation of B can never be 0. There is a limiting value. It's always greater than or equal to some limiting value. And that limiting value is proportional to the commutator of these two operators A and B. Okay, this is what the statement of the uncertainty principle is telling you. So basically, if you, for example, if you make one of the distributions look like the left one, and then the other distribution will necessarily look like the right one, because the product of these two standard deviations has to be some particular value. If you make the standard deviation of one as close to 0 as possible, so that it is very, very sharply peaked, like in the left-hand side graph, then the other distribution will necessarily be very, very largely spread. So this is the usual statement. So apply to the X and P operators. We will apply to the X and P operators in just a second. If you apply to the X and P operators, because X and P do not commute, this tells you that if you measure position very, very, very accurately, so that the position measurement is a very, very sharp peak, then you lose track of the momentum completely. Okay. So you might actually worry a little bit about the I in this formula, because the left-hand side is manifestly a real quantity. But it turns out that the commutator of the two operators also has an I in them and they get cancelled. Okay. So let us quickly understand how to do these calculations in the context of quantum mechanics in continuous distributions. Remember that if you have a continuous distribution, or if you prepare the state in some state psi, then the probability density, as you already figured out, is psi star psi in a previous tutorial. So for example, in QM, if you take the average value of x operator, this is nothing but, if you look at minus infinity to plus infinity, this is psi star x psi dx, okay? And for example, the average of x square is minus infinity to infinity psi star x square acting on psi dx, okay? Anyway, so on and so forth. You know how to calculate this, and the sigma square, which is delta x square, is nothing but x square minus x. Okay. So let us apply the notion of uncertainty principle to the x and p operators. So remember that this only means that those operators which do not commute cannot be simultaneously measured very accurately. If the commutator of A and B is 0, then of course sigma A times sigma B has a lower limit 0, which means I can make both the measurements very sharply peaked. There is no uncertainty in the values of these measurements. I can make the right hand side exactly equal to the left hand side if the two operators commute. I can make the left hand side graph and the right hand side graph almost similar if the two operators commute. Okay. So how does this apply to say the x and p operators? So sigma x square times sigma p square is greater than or equal to, the statement says this is greater than or equal to 1 over 2i times the average value of the commutator of x and p, the whole square. Okay, so let's evaluate the right hand side. You know by now that x times p is nothing but I h bar times the unit operator. Okay, so what is expectation value of xp? In any state, this is nothing but expectation value of IH bar times unity in any state, right? But this is just a unit operator. So this is expectation value is nothing but IH bar times minus infinity to infinity psi star 1 times psi is the same as psi dx. But this is nothing but the total probability, right? This is total probability, or you can also claim that this is a normalized wave function. So this is either way, this is equal to 1. Okay, so this whole thing is nothing but IH bar. So sigma x square times sigma p square is greater than or equal to 1 over 2i times IH bar, the whole quantity square, which is saying that sigma x square and sigma p square is greater than or equal to h bar over 2 quantity square. And since these are real quantities and uncertainties are manifestly positive, so I can always take the positive square root and say sigma x times sigma p is greater than or equal to h bar over 2. Okay, so this is the famous Heisenberg uncertainty principle applied to the x and p operators. But this statement is true for any set of two operators that do not commute. The answer of sigma a times sigma p would be different depending on what the answer to the commutator is. But for x and p operators, it turns out that sigma x times sigma p is greater than or equal to h bar over 2. Okay. So basically what this is saying is that the spread, so imagine the ideal measurement in quantum mechanics. We prepare a system and then we take the ensemble average, which means that we prepare billions of identical systems. This is an idealistic experiment, and you measure x and p. Try to measure simultaneously on this. Suppose if you measure x value very, very accurately, then the corresponding spread in the p values would be very large. If you measure p very, very accurately such that the value of momentum is very sharply peaked, then correspondingly, the value of x would be highly uncertain. It could equally well be 1 or 10 billion, right? So that's what it means. So when you try to measure one very, very accurately, you lose information about the other. This is the basic import of the uncertainty principle. Okay, all right. So let us line here, and then we'll continue talking a little bit about eigenstates. So what are eigenstates? Clearly, so if you go back and look at this picture that we drew, if psi plus is an eigenstate of A or an eigenstate of B, I am sure to get the value A plus or B plus, right? That's what quantum mechanics is telling us. There is no spread, there is no deviation, there is no probability. If I measure some operator on a system, and if so happens that system is an eigenstate of the operator, then I will get the exact same eigenvalue corresponding to that particular eigenvector. So there cannot be any spreads in measurement if I'm taking my expectation values in the eigenstate of one or two operators. So what does this mean? So let us say that there is some operator A, okay, and it has some eigen function psi plus. Okay, so let's calculate this standard deviation. Standard deviation I'll calculate by first calculating A square, and then I'll calculate the average value of A and take the square, and this would be a measure of the variance, and the square root of this would be the measure of standard deviation. But suppose if I am actually preparing the system in the state psi plus, which is an eigenfunction or eigenstate of A, then what happens? How do I calculate these guys? Well, A in that case is psi plus star A psi plus dx, right? But A acting on psi plus is nothing but A plus psi plus. So this is nothing but A plus psi plus star psi plus dx. But since I'm assuming that these are normalized states, normalized to unity, this is nothing but A plus. Okay. Now let us calculate A square. What is this? Again, sandwich the operator between psi star and psi. So psi plus star A square psi plus dx, which I can write as psi plus star A square is A times A psi plus dx. I have to apply A twice to psi plus. This is equal to psi plus star A. If I apply A on psi plus once, I get A plus psi plus dx, right? So this is A plus times psi plus star A acting on psi plus again, which gives me another factor of A plus psi plus dx. And again, I can pull out the A plus because it's just a constant. And I will have psi plus star psi plus dx is just 1. So this is nothing but A plus square. Okay. So the average value of A is A plus. The average value of A square is A plus square. So the standard deviation in A, standard deviation in A, if I prepare the state and eigenstate of system in an eigenstate of A, is nothing but A square average minus average of A quantity square, which is A plus square minus A plus square, which is 0. So eigenstates have 0 spread. Okay, so suppose if I prepare the system in some eigenstate of A, and if I keep measuring it, I'll keep getting exactly the same value over and over and over again. If I have another operator B that commutes with A, such that A and B have the same set of eigenvectors or eigenfunctions, I can keep measuring A and B in any order as long as I'm doing only A and B and not anything else and disturbing the system. I'm sure to not get out of the state psi plus at all. I'll simply get the corresponding eigenvalues over and over again. But if A and B do not commute, then my flowchart looks very different, and I have to apply the rules of probability to understand. The way you understand this from the point of view of the uncertainty principle is this. the spread in the values of a particular operator that you get, which is also a measure of the uncertainty, because the larger the spread, the larger is the uncertainty, right? So as possible, it's possible to get 1, it's possible to get 5 million, then there is a large uncertainty. So if you want a smaller uncertainty, you have to make the standard deviation very sharply peaked, like in the left-hand side blue distribution here. But uncertainty principle tells you that if you have two if you have two operators that do not commute, then it is not possible to simultaneously measure. Simultaneously is very important. Okay, I cannot measure both of these guys simultaneously very accurately. There is an inherent limit that nature puts on such observations. Notice that this has absolutely nothing to do with the experimental setup itself. The experimentalist could be extremely good. She could design the experiment very, very carefully and very, very accurately, but she or he would still not be able to escape this fundamental limit on observation that nature imposes on us. This is particularly only for two operators that do not commute. Okay, such operators for which the commutator of A and B is non-zero are called incompatible observables. So such pairs of incompatible observables can never be measured very accurately simultaneously. If you measure one very accurately, you are bound to lose information on the second, and vice versa. So this is the basic import of the uncertainty principle, particularly as applied to the X and B operators. But this is not the only set of operators. There are also other operators that share this uncertainty principle. As long as the commutator of the two operators is not zero, this law holds true. Okay. So for this lecture, we will stop here.